This presentation is titled Graph Neat Examples in Raku, Set 4. My name is Anton Antonov. Today is July 31st, 2025. In this presentation, we are going to discuss SVG plots, sparse matrix connections, and graph operations. Let me break the pattern here a little bit. So all of the important or the most important or most impressive example is probably summarized here. So you can see I'm making a hexagonal graph. I'm producing some difference of that hexagonal graph with a neighborhood graph from randomly picked vertices. Then I'm finding quickly connected components on another neighborhood graph from another set of random vertices, and then I use those to make highlights, to make this kind of highlighted plot, which I think it looks good or it's artistic. All right, so what are neat examples? They showcase a certain programming language or packages in it. So in this presentation, we are showcasing the Raku packages graph, and also to a lesser extent the package math sparse matrix. The visualizations are done with JavaScript D3 and GraphVis. So a GraphVis is actually it is a system which is separate from Raku. It is an old system. It's very easy to install its engines on any platform, any operating system. And the package graph knows how to generate the dot language specifications of graphs for GraphVis. And we can use this SVG code to render graphs. This is more or less what is happening here, right? This is an SVG rendering. So there's a natural connection between sparse matrices and graphs. And the sparse matrices, again, they're going to be visualized with JavaScript D3. So what is this neat example here? What is going on, right? And why I consider it neat? So we have the string names of certain graphs, parameterized named graphs. And these string names, they can be used with this Raku notation to actually invoke the corresponding classes and with a certain size argument to produce this dot specifications. So so what is happening here? If I disconnect or change this magic specification not to be a magic specification, just a comment, we see this is the SVG code. Now it becomes magic specification, and it's going to be rendered as HTML. If I remove these options here, we should be able to see the actual dot language specification. So the dot language is a specification for graphs language in GraphVis, the GraphVis system. And if I say here with the adverb as SVG, right, this is going to be rendered. I'm going to produce the corresponding SVG code, and that is automatically rendered in this Jupyter notebook environment. But I also want to have some other elements specified, like different engine to be used, not the default engine which is being used here. And so that's why we have this full set of specifications. Okay, and you can see, we have the cycle graph, the star graph, and the wheel graph. They're all obviously related to this size 8. So similarly, I can produce, let me just zoom out, several circulant graphs. Circulant graphs, they were relatively new when I was preparing this presentation, I think actually last year. And so if I remove this first argument, you can see we have 17 nodes, and we have certain jump, right? And this jump is, say, 3, 5, and so forth, right? So you can see from 0, we jump with 3 steps, we go to 3, then from 3 we go to 6, and so forth, right? But I think it looks better if I have this this kind of jump cycles, two types of jumps. Okay, with the circulant graphs, we are going to demonstrate the sparse matrix connection. There is an intimate connection between what happened here. This is annoying or embarrassing. Let me actually see. Maybe I missed rendering certain evaluating certain parameters or variables which are being used here. Okay, and you can see how these sparse matrices correspond to the circulant graphs I was showing above. The circle and graphs, they have this shape here. As I was saying, there's a natural connection between sparse matrices and graphs. One of the big reasons for me to implement the package math sparse matrix was the connection with graphs. Another one is a bigger one actually, is for usages of sparse matrices for data science analysis and exploratory data analysis. All right, we can extend this example with multiple named graphs, and this is what is happening here. So I have taken all of the named graphs except indexed and nested graphs because they use somewhat different initialization, and I have plotted them here. So the neatness of this example is that we have all these sparse matrices showing, showing the different named graphs. All right, I don't necessarily want to show this, but okay, this is using circle and graphs. We can do another way. We can display chessboards in another way. I have right now in Raku, we have 3 ways of displaying chessboards, and I have featured this chessboard display in some other presentations. I'm not going to expand on it. The JavaScript version, which is shown here, uses the Forsyth-Edwards notation. The other one, this here, the graphviz.chessboard package, it's a standalone package or separated package that uses graph to make the chessboards. And here I'm using matrix plot from JavaScript D3. Just by using the circle and graphs, I think it's a circle and graph which is being used. Yeah, it produces this type of visualization of the chessboard. You can see it here. There's a specially selected circle and graph, which, if we look at the matrix here, yeah, basically we choose the number of vertices and the types of jumps, how many and what numbers for the jumps, 3, 5, 7, for size 8, and then we display this matrix. All right, so the main example, or the most impressive example, should be this one. It's related to what I was showing in the beginning. Let me evaluate all of the steps here and make the visualization. You can go through these steps here if you want to follow them with the notation, mathematical notation being used, but I'm just going to exemplify it. I'm going to show what is happening. So first here, I'm making a regular graph. Let me remove the highlighting here. A regular graph, which is triangular graph, and so here it parameterized, and so regular grid graph. And then I'm going to pick randomly some vertices, find the corresponding neighborhood graph with distance 1 in order to produce some kind of nicer connected graph. And I want to make holes in this regular grid graph. So this is what is happening with this graph, the second graph which I'm making, right? And then I'm going to do something very similar to actually produce some artistic highlights. So this is what is happening here, and so yeah, just do the highlights, yeah. And this is rendered here with JavaScript D3. I can also render this with GraphViz, which is producing SVG, which is actually slow. First of all, the SVG code tends to be quite large when it is generated, in principle, right? Or maybe by specification, by design. And so here we have somewhat, I'm not sure, the plot is somewhat different, right? It's just a different way of specifying graph plotting. This here directly generates JavaScript code, which is rendered by this Jupyter notebook environment. And here we generate SVG code, which then again, it's rendered as HTML. So it's a different type of rendering mechanism. All right, I would like to summarize these features. As I said, this should be the most impressive example in this presentation. We're constructing a triangular grid graph. We can use also a hexagonal grid or any other kind of grid graph like rectangular. Then we are taking subgraphs. We have neighborhood graphs, graph difference, connected components, and then we display this in 2 different ways with D3GS and GraphViz via SVG. So there's a complete set of operations for graphs. We have graph complement, graph intersection, graph union, disjoint union. There's a graph product, which actually I haven't implemented, so it's not entirely complete. All right, so here another example related to this. I'm going to use a hexagonal graph, And so from this hexagonal graph, I'm going to find the middle point, just from the vertex coordinates, and I'm going to get subgraphs from it. And so here's the summary of the coordinates, and here is the middle point or mean point. And for different distances, this is from the package math distance functions. From using different distance functions, I'm finding different subgraphs and I'm displaying them. And again, like there's some kind of random removal and etc. being done here. So you can see I'm using the chessboard distance, Manhattan distance, and Euclidean distance. They're spelled out here. These are the actual functions or subs which are provided by math distance functions. And I'm basically taking subgraphs. Which the subgraphs have nodes or vertices which are within a certain distance from the mean point. Chessboard distance is also known as Chebyshev distance. Manhattan distance is also known as taxicab distance, and Euclidean distance is Euclidean distance. All right, so this was it. Thank you.